Okay, we are live now. Sorry for the delay. I was having some trouble with PowerPoint and then with Teams. And in fact, I haven't been able to create the PDF of the slides yet. I don't know, for some reason I keep getting the same error, but I will try and do it again during the break so that you can have it. As usual, here we have the Q&A. You are able to post messages, so feel free to post any question. I will keep an eye on the list and try to answer them as I see them coming. And well, there's nothing more. We are in part 3 of the methods block of the course. This is the last part. And let me just jump right into it. So, 1 second, click here. Here we are. Okay, so in the last lecture, in part number 2, we talked further into measurement, levels of measurement. What can we do with some variables and what can we not do? We talked about scales and the concept of populations and samples and how we typically study a sample and then want to generalize our results back to a population. So what is the problem with the random error? We talked about factors and how they can affect the dependent variables in different ways, and we talked about factorial designs. And today we're going to focus a little bit more about this part here, about what happens with the random error. How can we account for the random error when drawing conclusions from our study? And I want to go back to this one slide from part 2 to kind of refresh the concept of the sampling distribution and the standard error. By the way, I'm assuming that you can hear me and everything is fine. You can see my screen and everything. If someone can just post like in the Q&A list or on chat or whatever, just so that I know that it's working. So, okay, we had the sampling distribution. I don't see anything. I'm assuming it works. And yeah, it works. Okay, thank you. You never know what happens here. Okay, so we talked about the sampling distribution. So let's assume again that we are interested in knowing what the mean of a certain variable is in the population. So let's assume a certain distribution like this one here, and we're interested in figuring out what the mean value is of whatever variable it is. So in this case, we're measuring some kind of performance between 0 and 1. This is the distribution over the population, what we do not know. And over here is the true value, the true mean of the population that we want to find out. So if we run a study, it would typically do something like, sample n items from this population, make the observation and compute the sample mean, x bar. And what we saw is that depending on the specific sample that we have, sorry, depending on the n specific items, we're going to have a slight variation in the sample mean. So this x bar is going to vary a little bit over replications of the experiment. And the question is, so how much is it going to vary? And we had this illustration in which, let's say that we are sampling n equal 10 items. We make the sample of 10, we make the measurement, and we have the x bar. This is one replication of our experiment. If we do it again with a different 10 items, we have a different x bar. If we do a different 10 items, we have a different x bar. And the point is, what is the distribution of these sample means? So how much can we expect the sample mean to vary across replication of the experiments? This is the sampling distribution. And then a concept here is how much variation we have in the sampling distribution. We can measure by what we call the standard error. So what is the standard deviation of this distribution? If that standard error is very large, that means the sampling distribution is very wide. So we are expected to vary a lot across replication of the experiment. If the standard error is small, that means we are not expected to vary too much over replications of the experiment. So it should be fine. And in this case, we had here the example, if we only sample 10 items, we are expected to have quite a lot of variation. If we go up to 100, we are expected to have much less variation. So this is a way of controlling for the random error, or at least to quantify what the random error is expected to be. And so in this lecture, we're going to be going one step further, and we're going to talk about analysis in general, and we're going to focus on statistical testing paradigms. We're going to see a little bit of the history, how we come to test in hypothesis the way we do it nowadays, and then we'll talk a little bit more in detail about what it is for a certain result to be significant and whether it is relevant or not, and certain pitfalls of how we analyze data nowadays. So let's talk about analysis. Let me go a second to the queue and get rid of all these messages. Thank you everyone for letting me know. Okay, dismiss. Okay. All right, so once you collect the data, the first thing that you should do always is do descriptive statistics. So explore and plot your data, look for anomalies, look for patterns in the data, and make sure that everything is correct, that there's no apparent error. Everything is consistent, everything is how it's supposed to be. And always describe your samples. So things like central tendency, mean, medians, dispersion, correlation. Always try to describe what kind of data you got from your study. And it's important here to remember the levels of measurement. So what can you and can you not do with the variables, depending on how you measure them. And always plot histograms, scatter plots, box plots, tables, all kind of plots that are going to allow you to make sure that the data that you got looks to be okay. And in the coming lecture, we're going to talk about exploratory data analysis, which is all about precisely this, about describing data. And hey, just if you write some piece of text is also fine, and many times it's even better. So you don't need to just plot everything for the sake of plotting. Just try to describe. The whole thing is about describing what data you have. And especially if you're working with people and you have different subjects in your study, always try to describe what we call demographics. So that is, what are the properties of these people? So their age, where do they come from? Sex, what is their education background? What do they do for a living? That kind of thing. Everything that might be relevant for the purposes of your study. And then once we are past the phase of describing the data we have, we are going into the inferential part, in which we are interested in, again, making or drawing conclusions about populations based on the sample of data we have. So everything is about estimating some quantity, some statistic about the populations given the sample that we have. And so what we know is that there's always going to be some degree of random error, right? Depending on the specific sample, we're going to have some degree of error, and we have to account for it somehow when drawing conclusions. And again, if we have a very high random error or we have small samples, we are not going to be able to draw a reliable conclusion about the populations. We can say anything we want about the samples because we have the data about them, but we cannot say anything meaningful or reliable about the populations if we have too much random error. So we're going to see today how the random error is specifically going to affect our conclusions. And this is regardless of how much validity the study has. We don't care if you have perfect internal validity, external validity, constant validity, all that. It doesn't matter. If your sample is not good or is not big enough, you are not going to be able to draw any reliable conclusion, regardless of validity. And in the end, what we're going to see is that all the time, the significance of the effects we observe is going to be assessed with respect to the random error. And actually, we're going to see very nicely in some formulas, there's going to be something like the magnitude of the effect divided by the random error. Something like that is going to give us the significance of the effect we observe. Everything about the random error. And so let's say that we are focusing on the case of estimating a population mean. Let's say this is what we want to do. There is some concept or some variable of interest that we want to measure, and let's say we call it X. Whatever it is, let's say the height of people. Now, what we know is that the distribution of X in the population has a certain mean and a certain variance. We maybe don't know what it is. That is the point of the study. We want to find it out. But let's say there's a certain mean, mu, and a certain variance, sigma squared, in the population. Then what we know is that the expected value of this random variable, the expected value of the height, is going to be mu, and the variance of that random variable is going to be sigma squared. We know that just by definition. This is what we expect of any observation in our data. Now, if we compute the sample mean, like this, x bar, then it turns out that if you do the math, what we have is something quite simple. It turns out that the expected value of the sample mean is going to be exactly mu. So that means on expectation, over replications of our experiment, we are expected to have the same mean as in the population. And with respect to the variance, how much variability there is in the sample mean, what we have is that it's going to be the same as the original variance, the variance in the population, the variance in the original data, divided by the sample size. And so what this means is that, what we saw earlier in the sampling distribution, the larger the sample size, the larger n, then the smaller the variance, the smaller the variation in the sample mean. And from here we have the concept of the random error, the standard error is just the square root of this, which is what we saw earlier. And it comes just from the math. If you assume in the population we have a mean mu and a variance sigma square, then we know the sample mean is going to have expected value mu and variance sigma square over n. And here we see the effect of the sample size of n. Now, we know that the law of large numbers tells us that as we increase the sample size, then the mean that you observe in your experiment is going to converge towards the mean. So you're going to get closer and closer and closer and closer to the true value, to the mean in the population, as you increase your sample size. So the more data, the better. This is what the math is telling us. Hey, this random, this sample mean is expected to get closer to mu. That's fine. Regardless of the true distribution of the data, we don't care if it's Gaussian or gamma or beta or whatever. We don't care about the shape of the distribution. We know that it's going to get closer. Still, this is for only one single experiment. What can we expect? So somehow we need a model for the random variation in the sample mean over replications of the experiment. So we need a model for the sampling distribution. The law of large numbers, what it's telling us is that we are getting closer and closer and closer on expectation. But for any one given experiment, we have no idea of how close we are or even what to expect. So we have to account for the shape of the sampling distribution. And this is what we do, for example, with the central limit theorem. And so let's imagine we have this special case in which the original data, the variable in the population, is distributed according to a normal distribution. So let's assume that. Then it turns out that the sample mean, if you do the math, is also normally distributed. It also follows a Gaussian distribution. And it has, as we saw, mean mu and variance the same over n. Now, the problem is that, of course, we know Gaussian distributions are not very realistic models in our cases. There are certain times in which a Gaussian distribution is really not a good approximation. So let's say, for example, we have this distribution there. Imagine again, we're measuring the performance of some system, and in the population we have this distribution. Over here we have the true value of the population mean. This is clearly not a Gaussian distribution. So still, the good thing is that the central limit theorem tells us that as we increase the sample size, again, the distribution of the sample mean is going to be converging to a normal distribution. And again, regardless of what the original distribution looks like. So what this is telling us is that regardless of what this distribution looks like in the population, as we increase the sample size, the distribution of the mean is going to get closer and closer and closer to a normal distribution. And this is going to allow us, therefore, to make assessments of the random error and what to expect of the random error for any given experiment, regardless of what the original data looks like. So it's not only to know, as we saw earlier, that we're getting closer and closer to the true value, we are now able to quantify how close we are or what to expect. We are now able to start making inferences about the shape of this sampling distribution because we know it's approximately a Gaussian distribution. So, hey, until the late of the 1890s, everyone was just invoking the central limit theorem for basically everything because of the simplicity of working with Gaussian distributions. There were literally books with tables, huge tables of Gaussian distributions, just so that people could see the significance of their result, to see how much they expected the random error to be. So everything was like, assuming we have a Gaussian distribution, we do this and this and that, and this is what we get. And still, there are two problems. The first one is we don't know what the variance of the population is. We are not talking about it. And the other thing is, yeah, we know that it's going to converge to a Gaussian distribution as we increase the sample size, so as we tend to infinity. But what happens with small samples? What happens if in my study I only have 10, 20, 30, 50 observations? What can we expect? So this was the problem all the time. We're talking about approximations when computing or when quantifying the random error. And then something happened in the Guinness factory. And yes, it's the beer factory. And there was a person there who made a huge advance in the right direction. So let's talk a little bit about statistical testing. With a little bit of the history, I'm going to tell you a little bit of how we come to test data the way we do it nowadays. So this person in the Guinness factory was William Gossett. And he published this paper in 1908, I think it was. And he actually used the pseudonym student because according to his contract with the Guinness factory, he was not allowed to publish any research. So he just said, hey, I'm just some student who found out something. And so he published this paper in which we essentially have now what is the sampling distribution of the sample mean, assuming a Gaussian distribution, regardless of what the sample size is and regardless of what the variance in the population is. So again, with a little bit more understanding, what we saw is that Gaussian approximations are okay, but not for small samples, because everything is in the limit. As n tends to infinity, we know it's Gaussian, but what for a small sample? So Gossett started to work on the theoretical distributions of different statistics under a certain assumption of the data generating process. And specifically, when we assume that the data are normally distributed, they have a Gaussian distribution, then what he found out is this t-distribution. So that if we compute something like what we have here, so we have the mean of the data we have observed, we have some hypothesis about what the mean is in the population, then we have the standard deviation we observe in the sample, and here we have the sample size. This is going to be distributed in a certain way, and he derived the formulas for that certain way. This is what we call the student's t-distribution. And in a way, it's kind of accounting for how much uncertainty we have in estimating the population standard deviation with the sample standard deviation. So over here, we are estimating the sample deviation of the population based on what we observed in the data. And because this is, again, subject to random error, the t-distribution is in a way accounting for that random error. And so here we have a picture of what it looks like. So this t statistic that we compute, this t, you see that it's accounting for the mean of the population, standard deviation, sample size, and what you observe in your data. So that number over here has a certain distribution, a certain sampling distribution. And what Gossett showed is that if you have just a little bit of data, let's say only 2 points, you see the distribution is going to be wide. If you increase your sample size, let's say to 30 points, your distribution is going to get narrower. And so again, here we see the effect of the sample size. And so what he was doing is, hey, yeah, we know that in the limit, this is going to be Gaussian, but when we have small samples, this is actually the theoretical distribution. So we do not need to assume a Gaussian distribution anymore because we know this is how it's supposed to be distributed. And the whole thing about choosing the sample size equal 30, etc., by the way, comes from this distribution. It's the point where a t is more or less the same as a normal distribution. So anyway, we now have a sampling distribution or the theoretical model for the sampling distribution of the mean, and we can start quantifying how much variation we have. There was a guy called Ronald Fisher who then started working on this, and he actually provided the proof of the t-distribution very early, you see 1912, 1915, and he actually wrote this book about statistical methods. This was kind of a huge thing back in the day, and he proposed a certain methodology or certain philosophy for testing the significance of data. And what he proposed was the following. So let's suppose we observe some data X, and let's assume that it comes from a certain distribution that we don't know anything about, other than it has a certain parameter theta. So again, in the case of a Gaussian distribution, this could be the mean and the variance. We don't know anything about it, but what we want to do is test hypotheses about this parameter, about this data. And so what he said is we have this null hypothesis, it's called H0, in which we are going to test whether the parameter of the distribution that the data follows has a certain value. So let's say we could say something like null hypothesis, the mean of the distribution equals 0 or equal 1.2. So we are interested in testing this null hypothesis about the data in the population. Then the idea is we have to choose a relevant test statistic T, capital T, such that if we have a large value in that statistic, then that value is going to reflect evidence against null hypothesis. So in a way, it's measuring something like how extreme is your data. Given that statistic, we are able to compute what we call the p-value. And the p-value is nothing but the probability that if the null hypothesis is really true, so if, for example, in the population really the mean equals 0, what is the probability that we observe a sample of data with a test statistic that is at least as large as the one we have observed in our data? So what we have is our data here, and we can compute the t-statistic, whatever it is. And then what the p-value is, what is the probability that if we replicate our experiment and get a new sample, let's call it x star, and we compute the statistic in that sample, we get something that is even larger. So how extreme is our data under the null hypothesis? And then the idea is that if that number is very large, that is reflecting evidence against the null hypothesis because our data is too extreme under that assumption. So we can assess the statistical significance of the results and say if the p-value is less than some threshold alpha, let's say 1%, 2%, 5%, then we reject the null hypothesis. So we say we have enough evidence showing that the data under the null hypothesis is very rare. So we are going to take that as evidence against the null hypothesis, and then we reject it. So we reject this notion that the true population mean equals 0 in this case. And so see, in this case, what we have is the null hypothesis and maybe alpha, this threshold, are set before running the experiment. So we're interested in testing a certain thing, we collect the data and then look at it. And the outcome of this process is a continuous measure of the significance of your data, what we call the p-value. So the p-value is a property of our data under the null hypothesis. And so, you know, in the typical case that I'm all the time talking about, if I want to measure the height of people, I might have a certain hypothesis. I'm going to be able to say here theta that I'm interested in is the mu. I could do something like null hypothesis mu equal, I don't know, 180 centimeters. And then I go through the process. And if I find the p-value to be very small, then I'm going to say this is not going to be correct. There has to be something else. And then I can test another hypothesis, so on and so forth. So in the case of testing the mean, again, let's say I collect some data, these 10 observations. I'm going to assume a Gaussian model. I set my null hypothesis as the mean in the population equals 0. Then I choose the statistic, and this is the value of the statistic. So this is quantifying how extreme my data is. And then I get the p-value, which is 12%. Now, if I consider that to be small enough, then I would reject the null hypothesis. And just see here in the plot to understand what's going on. Over here we have the sampling distribution of the t-statistic or the z-statistic in this case. So this is the one modeling how extreme our data is. And what we're looking at essentially is at the tails of the distribution. So what the P is telling us is that the probability of observing our data or something more extreme is going to be either this side or this side of the distribution in the extremes. So this probability in red accounts for roughly 12% of the probability. If we get a p-value which is even more extreme, even smaller, then that would mean, for example, the p is over there, and so we are more extreme in the sampling distribution. So everything is about how extreme is your data under the sampling distribution of the statistic, assuming the null hypothesis. And so Fisher used the term significance level for this alpha, and it's just a reference point to consider a result significant or not. So we rejected again the null hypothesis if p is less than alpha. And of course, this is context dependent. It depends on the specific problem that you're looking at. It depends on your field. It depends on the data you have. And it's normal, or it was normal for him to change it from time to time in light of new evidence. If you're collecting more and more data, you might be able to just change the value of alpha. More or less, he arbitrarily suggested a 5% threshold. If you read the book, it was actually just to make a point, but he never suggested a 5%. Nowadays, everyone uses a 5% for some reason because of the book, but really he did not suggest anything. And it's important to keep in mind that if we observe a p-value that is larger than alpha, that doesn't mean that we prove or we accept the null hypothesis. We just fail to reject it. We are never accepting the null hypothesis. We will see about it later. So that was the Fisher philosophy. And then right after it, we had these two guys, Pearson and Niemann, which presented a different philosophy for testing. And how they called it is hypothesis testing. And the process here is a little bit different from Fisher's, but it kind of goes in the same direction. So what they said is, we define not only a null hypothesis, but also an alternative hypothesis. Pearson had this idea, which actually came from Gosset, that if you reject a null hypothesis, it's only because there is some other alternative hypothesis that makes the data more likely. And so they developed this framework in which we always consider two hypotheses, the null and the alternative. So for example, we could say something like the null hypothesis means that the population mean equals 0. The alternative is the population mean equal 1, something different. And so under this framework, we have to set what are the acceptable error rates in the testing. So there is an error rate called alpha, which is the probability of making a type 1 error. We're going to see what it is, and a probability beta of making a type 2 error. And so what they said is we have to choose the most powerful test statistic for this alpha and for the hypothesis, and that is going to define some critical value C, some threshold. And then the point is, given this hypothesis, given these errors, we are going to select the sample size that is going to be required for us to detect an effect of D or larger. So the point is, if this is what you want to test, and these are the errors that you're willing to make, now I'm going to tell you what is the required sample size N to be able to detect this effect subject to those errors. And then after this, we collect the data, however many observations we needed to collect. And similarly, we reject the null hypothesis if the test statistic on our data is larger than the threshold. So if our data is, in a sense, again, more extreme than this threshold, than this critical value. And so the testing conditions are set beforehand. What is the null hypothesis, the alternative, and the two errors. And the experiment is designed for a specific effect size. So we choose the sample size based on what is the effect that you want to test. The outcome here is a binary decision. You either reject the null hypothesis or you don't. So the outcome is not something like the p-value that has a certain magnitude. The answer here is you reject or you accept. That's it. Are you larger than the threshold or not? So let's take a little bit of more detail here. So imagine that we are again testing the mean, and in our data, let's assume the variance of the data equal 1. So this is how much they vary. In our study, we have collected only 10 observations, and our hypotheses are age 0, the null hypothesis. Let's say the mean equals 0, and the alternative hypothesis, let's say that it's 0.5. If we visualize it, then what it means is that in the null hypothesis here, the solid line, this is how the test statistic is going to be distributed. This is what we expect of the test statistic under the null hypothesis. And then under the alternative, here in the dashed line, we have what is the expected distribution of the test statistic. And then we have our data. We collect these 10 observations, we compute the test statistic, right? And that test statistic is going to be somewhere along this line. And depending on where it is, we are going to go one direction or another. And so the test statistic is going to be, again, the student's t distribution, or the student's t. We have here the sample mean. We have whatever hypothesis we have for the mean in the population. We have here the standard deviation or the variance. We know that it's 1. And then we have here the sample size, 10 in our case. So we collect our data, we compute the test statistic, and again, if this is less than alpha, then, if this is larger than the critical value, then we reject the null hypothesis. And so in reality, we have only 2 possible outcomes. So we either reject or not reject the null hypothesis. These are the 2 only possible outcomes of this testing paradigm. And in reality, only one of the 2 is correct. Either the null hypothesis is correct or the alternative hypothesis is correct. Only one of the 2 can be. Or actually, well, yeah, never mind. So if we reject the null hypothesis, and it turns out that that's correct, the alternative hypothesis is the one that is correct, then we have a true positive. It's a positive because we are rejecting the null hypothesis given the data, and it's true because, yeah, in reality, in the population, H1 is true. So this would be a case of a true positive. We are correctly rejecting the null hypothesis in favor of the alternative. We could also have a true negative. A true negative would mean we do not reject the null hypothesis. This is why it's a negative. And it turns out that in reality, the truth is the null hypothesis is true. And because we do not reject it, we are having a true negative. In this case, we were correctly not rejecting the null hypothesis. But of course, we could make a mistake. Let's say that if we make a mistake in rejecting the null hypothesis when it's actually correct, that's what we call a type 1 error. We incorrectly reject the null hypothesis. It is correct, but our data is so unluckily extreme that we reject it. And the opposite is a type 2 error, in which we do not reject the null hypothesis, but we should have, because in reality, the alternative is correct. This is what we call a type 2 error. We are failing to reject the null hypothesis when we should. So if we want to visualize it, the type 1 error would be this portion here in the distribution. And if you see, it's part of the null hypothesis, because in a type 1 error, the null hypothesis is correct. This is the true model, but our data is so extreme that it fell under this region here. And this probability is alpha. So what is the probability that our data is so unluckily extreme that under the null model is going to look like too extreme to accept the null hypothesis? So this is alpha, if we visualize it there. In terms of the type 2 error, it's actually here. It's part of the alternative hypothesis, because this is the case in which the alternative is true, but our data is not extreme enough to reject the null. So it's saying that we are actually in this part of the test statistic. Our data is not extreme enough, so it falls under this region, and it's this probability of making a type 2 error, because we are incorrectly failing to reject the null hypothesis. So I hope it's a little bit more clear what it is, the alpha and the beta. And by the way, what we call the power of the test is nothing but 1 minus beta. It is how likely it is that we successfully reject the null hypothesis when we should. So again, we collect our data, we compute the test statistic, and then we put it over here in the distributions. And depending on where we are, this would be the critical value. If we are larger, there's still this probability of making a type 1 error, of incorrectly rejecting the null hypothesis. If we are on this side, we are still with a certain probability making a type 2 error if we are not rejecting the null hypothesis. So what is the effect of the sample size? We see it here in the formula. And let's say now that instead of collecting 10 observations, we collect 30. So it would look like here on the right. And the thing is, the alpha would still remain the same. We set it to 5%, 2%, 1%, whatever it is. Now the point is the distributions are going to be narrower. We know this because we know that the sampling distribution is going to get narrower and narrower as we increase the sample size. So in a way, we are getting closer and closer to the true value of the population mean, and therefore it's going to be easier to test this hypothesis. So alpha is going to remain 5%. And now the thing is, the probability of a type 2 error is going to be smaller because we have more data, we are more reliable, we can make more confident conclusions. And if you notice, actually, the critical value is moving towards the left. So that means our data does not need to be that extreme because we have enough data to show otherwise, to show that the null hypothesis is false. So this is the effect of the sample size. The more data we have, this is exactly what's going on. I have a question. Isn't there a distinction between single and double-sided error considering rejecting the null hypothesis? Actually, yes. It depends on whether you test the hypothesis being something like mu equals 0 or hypothesis being one-sided. Then the alternative would be something else, and it would be about looking only at one side of the distribution or looking at both sides of the distribution. I'm not going to get into all these details. I'm just telling you about the whole framework, what it means and what is the effect of each of these constants. Okay, so this is the sample size. What happens if we have a different alternative hypothesis? What if we say instead of a mu equal 1 or 0.5? Yeah, 0.5. What if we say, hey, I think the alternative is smaller. So we are changing this number here. And by changing that, what we see is that the numerator should be larger, and therefore it should be, it's smaller, so therefore the t-statistic is going to be smaller. And so it's going to be harder to test one hypothesis or the other because the two distributions are getting closer and closer together in this case. And so it's going to be more difficult to tell one from the other. So what's going to happen here? Now, essentially, the distribution, the sampling distribution under the alternative is going to get closer to the distribution under the null. And the effect is going to be more type 2 error. More probability that if the data is not extreme enough, we are making a type 2 error. This is going to be the probability of type 2 error. Again, because the two distributions are closer and closer together. So it's going to be harder and harder to tell whether our data comes from one or the other. We are going to need more and more data to tell one or the other. And then finally, the other thing that could happen is maybe the variance in the data, something that we have no control over, maybe it's larger or maybe it's smaller. So let's say that instead of having a variance of 1, now we have a variance of 3. That means that the sampling distributions are going to be wider, what we have here. And if they are too wide, again, the two distributions are overlapping so much that basically under any circumstances, we are going to have a type 2 error. The data is not going to look like extreme enough to reject the null hypothesis. And so there's a larger type 2 error. if the variance in the data, in the original data, was actually smaller, then the distributions would be a lot narrower, and we would have a much lower probability of type 2 error. It would be much easier to see the or to reject the null hypothesis if we should, to see that really the alternative is correct. And so you see here in the T statistic, we very nicely see what is the effect of all these factors. What is the effect of our hypothesis of how much variability there is in the data to begin with, and how much data we have. We have how all those play a role here and there in the distributions. And so under the repeating experiments, the long run error rates remain alpha and beta. So if we have these binary decisions about rejecting or not rejecting the null hypothesis, then we know that in the long run, alpha% of the times we're going to make a type 1 error, beta% of the time we're going to make a type 2 error. And so again, there's really no suggestion here or no ground truth, so to speak. But Nima and Pearson suggested something like, let's have beta less than 20% and alpha less than beta. So there was something like saying you should have a statistical power of at least 80% of probability of correctly rejecting the null hypothesis if really you should. And then they developed the idea of what is the best test. And it turns out to be something like, which is the test statistic that subject to a certain type 1 error is the one that minimizes the type 2 error. So what is the most powerful test? That is the one that you should do. And happy coincidence in the case of testing the mean of a Gaussian distribution, it turns out to be student's T. So that thing that Gauss had developed years before turns out to be the one that is the most powerful under this framework. And so if we put side to side the Fisher philosophy and the Neyman-Pearson philosophy, we see clear differences. We see that Fisher revolves around the p-value and Neyman-Pearson revolve around the idea of the alpha level, the probability of making a type 1 error. So significance level and in both cases. So Fisher is actually testing the significance of data. It's a property of the data, while Neyman-Pearson have testing hypothesis, the null versus the alternative. So when we have the alpha, it's a property of the test. And so Fisher is kind of measuring evidence against the null hypothesis, and Neyman-Pearson have this concept of the type 1 error rate, incorrectly rejecting the null hypothesis. In the Fisherian philosophy, we kind of go for the strength of evidence. We take the p-value as the strength of evidence against a certain null hypothesis. And in the case of Neyman-Pearson, this is more focused towards decision making. So do you reject or not reject the alternative hypothesis? You go in one direction or the other. That's it. It's a binary decision process. And the thing about Fisher is that the p-value applies to a single experiment. So the p-value is a property of the data of the one experiment that you just run. Whereas in the other philosophy, we have this alpha, beta, etc. applied to replications of the experiment. So you are expected to have alpha errors, beta% of errors over replications of your experiment. But given just the one experiment, you don't have anything. You only reject or accept, but you don't have anything more. And so there was a lot of debate, and they were actually having these fights, the three of them. But in the 1940s, they were kind of merged together in statistical books. And then this new paradigm was kind of adopted by researchers around the planet. And what happened is that we put together Fisher, Neyman, and Pearson, and for some reason in the textbooks, they started to put them together. And what we have is what we do nowadays, which is a mix of the two that doesn't make a lot of sense, but anyway, that's what we do. It's called null hypothesis significance testing. And the idea is essentially put together the two, the significance testing of Fisher and the hypothesis testing of Neyman-Pearson. And this is what we do nowadays. We collect the data and set the hypothesis. Typically, it's going to be something like mu equals 0, or mu is different from 0. And one is the opposite of the other. So normally, either there is an effect or there is no effect. That's what we test. We set the significance level typically to 5% or 1%, select the test statistic, and then compute the p-value. If the p-value is less than alpha, we reject the null hypothesis, and if not, we fail to reject it, and that's it. So here, what we're doing is first setting very specific hypothesis. Second, using the p-value to compare it with the significance level of Neyman Pearson, and a bunch of other things that I'm not going to get into detail. But anyway, this is what we do nowadays. So let me give you an example. Let's say we have 3 groups or 3 treatments, 3 combinations that we want to look at. Let's say that these are the numbers correspond to different patients, and then we have treatment A, treatment B, treatment C, something like that. So let's imagine that here we're measuring days to recover, for example, or now something that is the opposite. Let's say here we're measuring the health of patients. So a large number should be better. And so the mean that we observe in treatment A is 5.5. The mean we observe in treatment B is 565. The mean we observe in treatment C is 6.2. So looking at these numbers, we would be inclined to say something like treatment C performs better than B because 6.2 is larger than 565, which does better than treatment A because the mean for treatment A is 5.5. Now, this is correct regarding the samples. If we get this sample of data, these are the numbers that we got, and therefore that statement is correct. But that's where we stop. We are not saying anything about the populations. And hey, the populations are what we are interested in the first place. So we have to somehow account for the random error. And the whole statistical thing is about quantifying the random error such that we can make conclusions about the populations. So we can do hypothesis testing in this case. And instead of doing it, I'm just going to stop here. We're going to have a break, and then we're going to see an example of how the whole thing would be for an example like this. Let's break here. Let's come back in, I don't know, 14 minutes. So 10 to 12, we can come back and continue with the lecture and see an example of hypothesis testing with real data. So let's break. Let's come back at 10 to 12. If you have any questions, again, post them in Teams, and I'm gonna see if I can produce the PDF now and send it to you guys. See you in a few minutes. Okay, we are back. And sure enough, PowerPoint crashed again. I just posted the slides on Brightspace, by the way. All right, so we had this example in which we wanted to compare three groups, three treatments, A, B, and C, based on the sample of data we collected in our study. And we saw here the sample means, and we are now interested in making inferences about the means in the populations. So how do A, B, and C compare to each other in the population? So we can go and do hypothesis testing. And for example, let's say we want to compare A and B. So what we would do is set two mutually exclusive hypotheses. Let's say null hypothesis saying the mean in A is the mean in B. They are the same. That would be their null effect. Both are the same in the population. And the alternative would be what we want to prove, namely the effect of treatment B or treatment A. So that means the population means is going to be different in A from B. We get the data, we run a test, let's say a t-test, and then get the p-value. If the p-value is less than our threshold, the significance level, let's say 5%, then we would be rejecting the hypothesis. That means we have a result that is statistically significant, and that means we have high confidence that there is a difference. If we get a p-value larger than alpha, then we have a non-significant result, and so we have low confidence about conclusions on the population. So given these numbers, we are rejecting or failing to reject the null hypothesis. So we have a significant or non-significant result. And we know that we can be right or wrong in rejecting the null hypothesis. If we incorrectly reject it, then we're making a type 1 error. If we incorrectly fail to reject it, actually this should never be accepted. This should be fail to reject. This is a type 2 error. And so what do we have in our data? Well, we state the hypothesis, let's say between C and B. We run a test for the difference in means, a t-test, for example. And what we get in this case is a p-value of 12%. Now, by most standards, this is going to be too large. So we are going to go ahead and not reject the null hypothesis, because 12% we consider that is too much. So this 12% is again a measurement of how extreme our data is. So we have a 12% probability of observing a data like ours or even more extreme under the null hypothesis. 12% is not so low, so we are not going to reject the null hypothesis. It could still be possible that the null hypothesis is correct. And so that's it. We failed to reject it. We are not going to say or to claim anything about the difference between C and B in the population. And just to be mindful, this is not the probability that the null hypothesis is correct. It's the probability that under the null hypothesis, we have our data or something more extreme. So do not confuse this 12% with the probability that H0 is true. That's not what we're measuring. So in the case of C versus B, we do not have enough evidence in our data to claim a difference in the populations. There's too much random error compared to the size of the difference. If we compare C and A, we would go and do essentially the same thing. And in this case, we get a p-value of 3%. Now, by most standards, this is going to be small enough. There's only a 3% probability that we would have observed a data like ours under the null hypothesis, so we are going to reject it. And in this case, we are going to claim that there is a difference in the population between C and A, given the strength of the evidence shown by the data that we collected. And so it's unlikely that these differences we observed in the sample appear just by chance. So it's still possible that we are just being lucky in our data, that we have some extreme observations, but it's very unlikely. So we go ahead and reject the null hypothesis. But keep in mind, it's still possible. Maybe we are making a type 1 error and incorrectly reject the null hypothesis. So this would be how we approach the problem of statistical testing, hypothesis testing, in a case like this, in which we want to compare group A versus group B. It will go something like this: the p-values, hypothesis, reject or fail to reject. Let's talk a little bit more about statistical significance and relevance, the relevance of a result. So what we see is, again, we reject the null hypothesis, and that means that we can have some confidence that treatment C and treatment A are different in the populations, in whatever target populations we are interested in. So in the populations, the means are different. Now keep in mind, it does not tell us how much difference there is. It's just saying there is a difference. It's just saying they are different. It does not tell us that the difference is important, whatever that means. It does not say that it's important for our problem, for our domain. It's just say there is a difference. It only says that the data is unlikely under the null hypothesis. And hey, maybe the data is also unlikely under the alternative hypothesis. Maybe we just got a very strange sample. And remember from the previous lecture, this could happen. The fact that we are, for example, doing random sampling does not ensure that our sample is going to be representative. It ensures that it's going to be representative on expectation over replications of the experiment, but given just the one sample, there's no guarantee, there's no certainty. So, hey, maybe we just got a very weird sample, and that's the whole thing. What we see with the p-value is that it's unlikely, but it could still be possible. So the thing is that as we get larger and larger samples, as we increase n, we are more likely to obtain a small p-value. And we could see that in the very formula of the t-statistic, it was something like this. Just by increasing the sample size, we are going to increase the t-statistic. And so, hey, we're just going to get a smaller p-value. And at some point, we are always going to get a statistical significant result if we just get more and more and more data. It's just a matter of how much data you need. Eventually, you're always going to get a statistically significant result. And the point is that it's going to be statistically significant if the p-value is less than alpha. And also consider that the alpha level, this 5%, is completely arbitrary. In some fields, it's 5%. In some other fields, it's 1%. In things like social sciences and psychology, you might be fine with an alpha of 20% if what you're finding is might lead to something big, to some nice discovery. In particle physics, you use an alpha very, 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 very small. You want to be very, very, very certain that there is something. But still, regardless of p, regardless of alpha, regardless of the sample size, regardless of all that, the true difference between the two groups, between A and C in this case, it is what it is. The true difference in the population is whatever it is. We have no control over it. It doesn't depend on p, it doesn't depend on alpha, it doesn't depend on n. It only affects our ability to detect such a difference. And so maybe it's a better idea to not just look at the p-values and make this binary decision of rejecting or not rejecting the null hypothesis, but it's more useful to report some measure of the uncertainty that you have in your measurement. So for example, the standard error. Yes, this is my observation, this is the sample mean, and this is how much variation we expect in the sample mean. Maybe this is more useful. Maybe it's even more useful if you couple all this into a confidence interval and say, hey, this is an interval that we expect contains the mean with certain probability. So there is the point of practical significance. With the p-values and then this whole hypothesis testing framework, we're only testing yes or no. But we have to go beyond that. It's not only yes or no, it's how much. And again, we could do confidence intervals. So I'm going to show you here for the sample mean, but really it's for any other statistic. You can do confidence intervals on whatever statistic you're interested in. And the point is, a confidence interval will be an interval containing part of the sampling distribution with some probability. That's what we call the confidence level. It's usually something like 95%, 95%, things like that. And so for a mean, we would be saying that our estimate of the population mean is going to be the sample mean we observe plus minus some length. And this is going to define the interval. And that length is going to be a function of the standard error, you see here, plus a constant. This constant is going to be dependent on how much confidence do you want. If you want a very large confidence, then that z is going to be large. If you are not interested in so much confidence, then that Z is going to be small. And the effect is going to be having a larger or smaller interval. And so in the case of our data, what we have is our estimate for the effect of A is going to be the mean of A plus minus this number. This is going to be determined by the fact that we want a 95% confidence interval and the standard error of A. And it turns out to be this interval here. We might be interested in, the confidence interval for B, and the interval would be this one here, and the same thing for C. And apparently someone is doing something in their office, and I think you can hear some noise. Anyway, if we go this line and compute the confidence intervals, here these intervals are quantifying two things. First, the estimation of the effect, so how large do we think the effect is of A, plus a quantification of the random error in the form of an interval that is expected to contain the true value with a certain probability. And so what we notice here is that all these three intervals overlap. So what this is showing is we might not have enough evidence to tell the difference between A, B, and C, because if you look at the intervals, which again quantify somehow the magnitude of the effect and the variation that we expect, they're overlapping. So this means if you replicate your experiment and you get different data, you might have them all being more or less the same, or even have a different order, like A, it's shown to be the best, followed by B and C, things like that. And just to say a little bit more visualization of what the confidence interval is, the idea is that if you plot the sampling distribution, centered at whatever statistic you have, the confidence interval, if we want, for example, a 90% confidence interval, what it's doing is having this 10% here, 5%, and 5% here, and this would be 90%. So it would be giving us this interval over there. It's the interval that is expected to contain the statistic of interest 90% of the times across replications of the experiment. If we want a 95%, then the interval is going to get a little bit wider. And so now we're going to have only 2.5% here, 2.5% there, and we are going to account for 95% over there. So this is what the interval is doing. And it all comes from how much confidence you want to have and how is the variation of the sampling distribution. So this is another alternative that we could go when being able, or when we are interested in testing hypotheses or testing how much confidence we can have in our data, in our conclusions. And at some point, if you think about the null hypothesis that we have in this hypothesis testing framework, you might wonder, isn't the null hypothesis false anyway? And the thing is that almost always there is a true difference. If you think about it, you're comparing the mean of some variable in populations between group A and group B. What the hypothesis is saying is that that mean is exactly the same. If you think about it, what we're saying is null hypothesis, mean of A, exactly the same as the mean of B. Exactly the same. Now, most likely this is going to be false. Maybe the difference is very, 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 very tiny, but it's not exactly the same. And so what we are testing with this framework is something that we know almost by definition, and actually in some cases is false by definition. The null hypothesis is false. So what is the point of going to, get the p-value, compare with alpha, reject, fail to reject, and everything, if we know that it is actually false by definition? And in practice, if you think about it and you go this philosophical way, it's actually like this. We don't make type 1 and type 2 errors. What we make is what we call type S and type M errors. So it's actually we make an error with respect to the sign. So maybe we say A is better than B, when in reality it's the other way around. If you look at it, and that is the alternative hypothesis, the hypothesis don't say anything about which one is better. They just say, are they the same or not? And then we make this directional conclusion saying A is better than B based on what we observe in the sample, based on this number. And so we could be wrong with respect to the sign, and we could be wrong with respect to the magnitude of the difference. That's what the confidence interval is quantifying in a way. It's quantifying the magnitude of the difference plus minus standard error. In the p-value, we don't have that. We are confounding the magnitude of the effect and the sample size. So in reality, very rarely we commit type 1 and type 2 errors. What we make is type S and type M. And so we had to consider how much power we want to have, how likely we want to be able to detect effects of a certain size. We have to worry about the effect sizes, about the magnitude of the effect, not just the p-value. And so, again, we have the type 1 error, probability of incorrectly rejecting the null hypothesis, and conclude there is something when there is nothing. It depends on the significance level, and this is typically the one we care about. This is the one we always control because we set it to something like 5%. It's fixed. But we have this type 2 error. What is the probability of fail to reject and conclude there is no difference when in fact there is? This one depends on the sample size, mostly, and is one that basically no one cares about and is not controlled for. In the original Neiman-Pearson philosophy for testing, the sample size was determined as a function of beta. So what is the probability that you want to have of making a type 2 error? In how we do it nowadays, in this whole null hypothesis significance testing framework, we don't do this beforehand. We usually check it afterwards, if we check it at all. Most people don't check it. If we have a negative result, we fail to reject the null hypothesis, no one basically is going to check the sample size. They don't care for what the beta was. And this is what we have to care about more often. It's not just about fixing this probability of type 1 error. It's about checking what is the probability that you have a type 2 error. Virtually no one does these things nowadays. And in any case, it depends on the data. So a lot of people say, I have so much data that if I really don't see anything, it's because it's too small. I recommend you go to this site. There's this tool called GPower, which has a lot of different tests built in, and you can check calculations for sample size. So you can go ahead and say, this is the kind of data that I have. These are the hypotheses that I wanted to test. Tell me what is the sample size that I require in order to observe a certain effect. Or if this is what I got and I failed to reject, tell me what is the power of my statistical test. So what is the probability that I'm making a type 2 error? Just go ahead and take a look. And going back to this question we had in the previous lecture, if you remember, we had this, what is the appropriate sample size? So if I'm designing my study, how many observations should I get? I know that the more observations, the better, but it's going to be too expensive. So what is the sweet spot? How many should I collect? And then we saw why this n equal 30 doesn't make any sense. And if you remember in the last lecture, I told you it depends. It depends on your data and it depends on what you want to find. And now we are in the position of going into the solution with more detail. And it's actually something like this. If you have previously estimated what is the variability in your measurements, so what is the sigma, or you know what the sigma is based on literature or something else, if you are somehow able to estimate what the sigma is, the sample size should be as large as it would take for the specific test to detect an effect size or an effect of a certain size with a certain probability. So over here we have alpha, we have beta, we have sigma, we have n, and we have the effect size. You see, it's more complicated than just saying a number. It depends on what you want to test and under what conditions. So let's say if we estimate some from some previous data that the variability in our data is 1.4. This is an estimation for how much variation there is in the population. Let's say it's 1.4. Let's say we are interested in detecting an effect of at least 0.3. So 0.3 or larger. And we want to do it with an 80% probability. That means the beta, we want to set it at 20%. And we are willing to accept a 5% probability of a type 1 error. So that is alpha equal 5%. Then there's a certain calculation that a tool like GPower is going to do for you. If you do the numbers, it turns out the solution is n equal 343. And you see, again, it depends on multiple factors. What are the probabilities that you are willing to accept of being wrong? What is the minimum size of the effect you want to observe? And what is the property of your data? What is the variation? Only then you're going to be able to start quantifying how many observations you need. In this case, it will be 343. And you can do this for multiple tests, multiple hypotheses, multiple effect sizes, etc., etc. So you see, the solution was, it depends. It depends on how confident you want to be. It depends on the kind of data that you have. And so just to summarize in a couple of quotes that I really like, one of them is the p-value is meant to be a detective, not a judge. If you think about it, the p-value was meant to give you an indication of the significance of your data, how extreme your data is under a certain null hypothesis, regardless of any betas, of any alternative hypothesis or anything like that. It was just meant to be a detective, something that would make you raise your eyebrow and say, I have something here. I have to continue studying. It was never meant to be a judge to say yes or no. It was only meant to be a kind of detective. And the other one is saying the p-value is just a test of the sample size. And this is very much right, because the only thing it takes for a p-value to be small is a larger sample size. Regardless of whether there is an effect or not, regardless of what the properties of the data are, it's just about increasing the sample size. So the p-value really is testing whether the sample size you got is enough or not to detect the effect. But that's it. And so the problem nowadays with this whole statistical testing framework is that if you carry out your study and for whatever hypothesis you find that the p-value is larger than alpha, this study is not going to get published. It's going to get lost. No one's going to care about it because it's a negative result. So the problem is that these research hypotheses are taken as false. Whatever you had is taken as false. And what we know is that, hey, maybe you just were unlucky with your sample. Maybe your study did not have enough statistical power. Maybe you needed to have a larger sample size. Maybe you just have a type 2 error. This is going to be taken as false. And on the other hand, whenever you got a positive result, a p less than alpha, it's going to get published and it's going to be taken as true. So replication is not rewarded. And the whole idea of statistical testing, if you remember from a few slides ago, it's about replication. Alpha and beta make sense over replications of the experiment. Given just the one experiment, we cannot claim really anything, for sure. And this is the whole idea of science. You are expected to replicate studies to see if we all get to the same results, yes or no. And so again, maybe you just got lucky and you just published something that is really not true, but it was just a lucky one. And so new knowledge is being accepted on the basis of single experiments. And as Fisher said, no isolated experiment, however significant in itself, is going to be enough for demonstration of any natural phenomenon. We need to go and replicate experiments to see how often we observe this extreme data. And the null hypothesis significance testing framework is not really well understood by senior researchers, so let alone by junior researchers or students. And this is a problem that we see very often in things like master thesis. As someone said, it's the most boneheaded, misguided procedure ever institutionalized in the rote training of science students. And everything is about misunderstanding what we really do with the p-values. So if you think about it, imagine the body of all possible studies that you can conduct in your life. It's something like this. Only a few of them are going to be interesting for your field, right? We could do a lot of studies. Many of them are going to be irrelevant. Some of them are going to be interesting for our field. And at some point, if you start computing the numbers and get the p-values and everything, you're going to see that those are the ones that are going to be statistically significant. They're going to be a subset over there. And sure, everyone wants to be over here. That means you are making a good discovery, something that is going to be relevant, and you can have a certain confidence that the result is correct. But you're going to find a lot of research that is just over here, was underpowered, a lot of relevant research that is just being not published because they do not have enough sample size, and a lot of research that is actually being published and it's completely useless. And this is what I want you to remember from this lecture. The fact that something is statistically significant, that doesn't make it important or relevant, or the other way around. And it's up to us to try to determine that based on the other multiple factors that we have seen in the past 3 lectures. And there's the point of choosing a statistical test, because we know different hypotheses are tested with different tests. If we are testing the mean of the population, then there's a certain test for that. You can also test the standard deviation. You can test the maximums. You can test many other things. Depending on which kind of test you have, which kind of hypothesis you have to choose a test. And all tests make different assumptions. Things like they assume a Gaussian distribution, or they assume at least that the distributions are symmetrical, and they assume random sampling, etc. So the point is, always you have to choose the, let me put quotes in here, correct type of test for your hypothesis and the assumptions, but then do not worry too much about the assumptions, because the test assumptions are kind of never hold in practice. We never had truly normal distributions. We never have truly random sampling. We're kind of there, so there's really no point in being picky about it. And so if you think about it, systematic errors due to sampling, due to how we measure, think about constant validity, think about external validity and all that, they are usually much larger problem and they are ignored. All we care is this p-value, and the p-value after all comes from a sample, and it comes from a specific way of measuring. If we are sloppy in how we measure and how we collect our data, then what is the point of looking at the p-value below or above a threshold? It doesn't make any sense. So for the point of choosing a statistical test, here you have online guides. You can go ahead and it's going to ask you different questions about what kind of data you want to test, and it's going to end up with a solution for you saying you have to run this specific test. And of course, there's many software available for it. You just have to call the right function, and that's it. You get your p-value, your statistic, and everything. And so for a specific case of testing the means, which is what we are typically interested in, we have multiple options. We have been talking about the t-test, which assumes Gaussian distributions. If you do not want to assume Gaussian distributions, then we have something called the Wilcoxon test, which is going to assume the distributions are at least symmetrical, but not Gaussian. So you can, in principle, use it in a larger context. Then we have something called the sign test, which essentially disregards all magnitudes, and it just looks at something like coin flips. So is A better or worse than B across observations, and that's it. And then we have something more advanced I'm not going to talk about, bootstrap and permutation tests. Those are more advanced statistics. So they are generally going to produce slightly different results. The p-values that you're going to get from these tests, even though they're testing the same hypothesis, is going to be slightly different because they're based on different assumptions. And the thing is, how much of a problem it is to have those differences is completely up to the researcher. And what I personally always suggest is run multiple of them, run like the t-test and the Wilcoxon test. If they agree with each other, then fine. If they disagree with each other, then look closer to your data and collect more data because there is something going on. And everything in the end is about analysis models. All these tests, again, are based on some kind of model. And so there's no point in blindly trusting the numbers and blindly trusting the p-value below or above a certain threshold. We should not let the assumptions of the model limit the kind of questions we ask to our data. And we're going to see about this in lab number 5, where we're going to see how to analyze some data. You're going to be able to learn a lot more from your data if instead of focusing on this hypothesis testing framework, you just try and explore it. Refine the questions that you're going to ask to your data. And only after finding the right questions, we are going to be able to do inferential statistics. But it's more important to make sure you're asking the right question. And our models should exploit the structure of the experiment. So think about controlling for other factors. If you just get, a bunch of data and do the test, maybe you are just ignoring other factors that you have to control for. Maybe you are ignoring a possible way of reducing the random error. There's many different ways that can go on into the testing procedure and are going to allow you to have more confidence in your results. And again, in Lab 5, we're going to see examples of this. So it's not just, you get your data and you test the hypothesis. You have to build a model for what the data is supposed to be, and then you test the hypothesis. We're going to talk plenty about this in the regression lectures. And meaningful questions here rarely have a yes/no answer. The answer is normally not accept or reject the hypothesis. It's not yes or no. Meaningful questions rarely have a yes/no answer. It's going to be yes, but, or in these cases, or it appears that, etc., etc. There's always going to be some degree of error in there, and our solutions, our answers to those questions have to be according. And just to remind you, if you remember this, absence of evidence is not evidence of absence. The hypothesis testing framework allows us to reject the null hypothesis in favor of the alternative. But if we fail to reject it, that doesn't mean that we accept the null hypothesis. We are failing to reject it. So what it is saying is, if there really is an effect, it's too small to be detected with the current data that we have. That's what it is saying. If there is something really, there is too small to be detected for now. Maybe there's no effect. I don't know. Maybe there is. We don't know. Just the whole point. We are failing to reject. We are never accepting. So a hypothesis about the absence of an effect cannot be tested. We can never test, statistically speaking, that a certain hypothesis about the absence of an effect is true. We are never going to be able to do that. We are going to be able to reject it or fail to reject it, but we are never going to be able to accept it. And so if you run a study and you have a null hypothesis saying, hey, there is no effect, and you get a p larger than alpha, you do not prove that there is no effect. The only thing that you have is a fail to reject. You do not have enough evidence to say otherwise, but you are never accepting this. And to finish, I just have a few slides with some of the pitfalls of statistical testing in general. I'm just going to go through them very, very quickly, but you're free to just spend more time on them. And again, it's more about preventing you from making the kind of mistakes that we always make when looking at statistical testing. And it's all about this. So what is it that we have in a p-value? If you look at the p-value computed with the t-statistic, for example, it's something like this. It's confounding the effect size and the sample size. This is what we care about, and this is something that we are controlling. Unfortunately, it's confusing the two of them. And so we have to be careful with how we interpret the p-value. Virtually never we check the power of the study. If we see that we have a p-value larger than alpha, very rarely you see people actually checking, are we expected to have a positive result or not? And it's kind of easy to achieve significance again if you just get more data. Think about it, keep it in mind. Mu and sigma, which are properties of the data, you have no control over. They are just what they are. They are properties of your study, of the phenomena that you're studying. You cannot do anything about them, and they're affecting here and here. The specific sample mean you get from your sample, you cannot change it. It is what it is. You just make some random sample, you compute the sample mean, and this is what you got. You can do nothing about it. That's over there. The only thing that you can control is the sample size. This is the only thing you can control. So the data, if it's unlikely under the null hypothesis, maybe it's also unlikely under the null, or sorry, under the alternative. We just don't know. So again, don't ever accept the null hypothesis. And keep in mind that you're only controlling the sample size. We will see in the regression lecture how to control for other factors, such that we are going to be able to have a statistically significant result after controlling for the effect of other things. And essentially what's going to happen is that this variance is going to be reduced. at some point we have to factor in the probability of having the null hypothesis or the alternative hypothesis. I'm not going to stop here, but essentially, if we can have a more Bayesian approach towards the whole thing, Bayesian as in Bayes, we could start considering what are the probabilities of the hypothesis being correct or wrong in the first place, and we could try to arrive at something like what is the probability of the hypothesis given the data. In the whole statistical framework analysis, what we have is the other way around, or something like what is the probability of p less than alpha given the null hypothesis. So if we go in a Bayesian direction, we might be able to do it the other way around. And this is ultimately what we are interested in testing the hypothesis, not testing the data. And again, consider that the null hypothesis may be always false by definition. So it's just that the effect might be very, very, very small, but no one cares about it. There's no relevance of it. So these binary accept reject decisions don't make sense. It's about, do we have enough power to detect a certain effect size or not? So we have to care about the sign and the magnitude of our conclusions. That's what we should do. And really, there's nothing wrong with the p-values. It's something with how we use the p-values. Remember, the p is meant as a detective, not as a judge. Care about the type 2 errors, and care about researcher degrees of freedom. During the whole study, there's many decisions that you have made on your own about what you measure, about how you sample, and all this, about which test you choose, etc., etc. But those decisions are not factored into the p-value. The p-value is just a number that you computed based on so many decisions during the process. What about those decisions? How do they affect your conclusions? This is what we call the researcher degrees of freedom. So how are all these decisions affecting your conclusions? Think about it. What are other sources of variance? Third variable problems. And why not quantify the effect size and the random error? You can do intervals, you can go Bayesian statistics, etc. And there's assumptions everywhere. All these models are based on assumptions. So be aware of the assumptions and just, conclude based on the assumptions. Look beyond the experiment that you have at hand. Try to get more data. Try to do error analysis. Try to see what's going on in the data to try to better understand them. And then you're going to see whether the test assumptions are kind of correct or not. But all assumptions basically are going to be wrong. So why use any threshold? Why use any alpha? Why not just take p as it is? And the key is replication. Both Fisher and especially Neiman and Pearson advocated for replication. It's just going beyond the one study. The p-value that you compute is only about your current study. You have to think beyond that and try to replicate your study. Try to get more data and see what happens, because all this statistical framework makes sense only in the long run. And that was it for this lecture. It was about statistical testing in general, right? I have a question here. When we talk about significance and sample size, does that connect to one of the points in your earlier lectures where you said that if you torture data long enough, you will find something? Exactly. If you have a big data set, and this is what we usually have, and if you think about it, this course is called Data Analytics. So the course actually should start now. When you receive a huge data set with thousands of variables, millions of observations, and they ask you to look at the data and gather some insights about the data or answer some research questions. Then if you do not see these first 3 lectures, you're very tempted to just go ahead and run a test and say, there is something. But you have to think about where the data comes from and what are the possible pitfalls of doing statistical testing like that. And in the end, if you keep comparing, like in the case of means, if you keep comparing the means of 2 different variables, you're going to find something eventually. Things just happen, and it's a coincidence. And you have to be prepared to detect whether you have a coincidence or not. So whether something is just spurious or not. That is precisely what we were saying. And the larger your data sets, the more likely it is that you're making that kind of mistake. So you have to be prepared for that. And so take-home messages are, of course, first, carefully analyze your problem and clearly state your hypothesis. Think very hard, very clearly about what is it that you want to study exactly. Identify the measures, the variables and how you're going to measure them. And then you design a study to validate your hypothesis. You only get into the design phase after identifying what it is that you want to study. And think thoroughly about the assumptions and what can go wrong in that design. You run the study, and then you analyze your data. Look for extraneous data, anomalies, run statistical tests, but don't get too crazy about which one and assumptions and all that. Think about all the possible errors that are being made before there. And as I say, type 1 errors make you lose money, but type 2 errors make you lose your job, and they're often neglected. The example I will give is this volcanologist in Italy. They were unable to say that the volcano was going to explode or something like that. So they were actually making a type 2 error. They were fired, and they were actually, they were sued and they went to court and everything because they failed to detect that about the volcano. If you just say, hey, something's going to happen with the volcano, and in the end it doesn't happen, then you're losing money, but you don't lose your job. So you have to think about what are the consequences of making an error in one or the other direction. And in the end, it's about being very careful about what you conclude from your results. Pay special attention to threats to validity, argue why your results are valid and what limitations they have. And do not fish for significance. This is what we were saying earlier. State your hypothesis beforehand and not just look for hypotheses based on what you see. And again, really the problem 100% of the times not, but 99% of the times is not with how you run your study. It's about how or what you conclude from your study. That is the key. How far did you go in your conclusions given what you have done? And of course, I'm going to finish with a comic. So, jelly beans, these goodies that you can eat, there's this person saying they cause acne. So, of course, they call the scientist and ask them to investigate. And so they run the study and they see no link between jelly beans and acne. And they have a p-value larger than 5%. Therefore, we fail to reject the hypothesis and say we didn't find anything. And then someone comes over and say, but I hear there's only a certain color that causes that. And so, they're going to investigate again. And they check whether there is an effect of purple jelly beans, brown, pink, blue, teal, black, etc., etc., etc. And of course, eventually, one of them is going to pop up, and it's going to have a p-value less than 5%. But it's just pure coincidence. It's just you were lucky or unlucky with that specific sample. And that's it. You conclude, hey, what? Out of the 20 experiments that we ran here, only one of them was found to be positive. What is going to be in the news? Green jelly beans are linked to acne. 95% confidence, scientists, whatever. This is most likely just a type 1 error. And this is the case in which if you keep testing the same hypothesis with different data, eventually you're going to find one sample that was unlucky enough to give you a positive result. This is what we call repeated testing, and it's a problem of its own. So never, never, never do that. And think about this kind of thing when you read the news. These things happen all the time. And so that was it. That was the final lecture of the methods part. You see, my idea was to show you that there is a lot that can go wrong in analyzing data. And if you think about this summary over here, normally your job starts here in analyzing data. But it's very important that you are aware of all this. Most data analytic courses start here, and that's why we want to start earlier, to be aware of all the pitfalls in these decisions over here when you're just, by the end, drawing conclusions. So I hope it's useful, not only for this course, but in general. And that's it. From now on, we're going to start with this part, with analyzing data. And the first lecture is going to be about explorative data analysis. that will be next week. And I think this is all for now. We're a little bit over the time, but I think it's fine. If you have any questions, again, feel free to ask. I will try to read again. And we are on Brightspace in the forum. You can always send an email. And as soon as I get the recording from the lecture, I'm just gonna post it on Brightspace. So I'll just wait a few minutes here in case there are questions, and if not, see you next week. Bye.